I'm going to present today a work that we have done recently in ITASCA in the office in France about a construction of a urban station in a highly urbanized environment. The work has been done for EGIS, it's a consulting firm in France, and he acted as the project manager. So we did the job for them. Before starting, I just want to acknowledge my colleague Tran, who many of you may know. He did most of the work that I am presenting, and he did a great job. Okay, so we are talking about the station is called Porte Maillot, and the station Porte Maillot is part of the EOLE project, or in French is EOLE, which stands for Est-Ouest Liaison Express. Donc, in English is East-West Express Link. And what is it? It's a project for modernizing the public transport in the Paris region. And together with the Grand Paris project, it has been the largest transport project in Europe in the last years. So the EOLE is the project that we are looking at. Consists of an extension of 55 kilometers to the west of the Paris town, where Paris is located here. And you have these 55 kilometers of train line that is extended to the west. So as part of this extension, we have 47 kilometers of new line and station, and 8 kilometers of new tunnels. And in these 8 new kilometers for tunnels, we have the 3 new stations, one of which is the Porte Maillot. So you see here, the Porte Maillot is the one there. And it is about this station that I'm going to present our project and some of the results. So once this project will be finished, it will serve 650K daily passenger. So it's an important infrastructure for Paris. And all of these projects have also been developed late in the last year because of the coming Olympic Games. So that we started this summer in Paris. Okay, so the Porte Maillot station. The Porte Maillot station is located in a region where we have a lot of existing urban structures. So we have a metro line here you see in yellow. We have train lines, 2 train lines here, tunnels. Then you have several car infrastructures, so a corridor, here a tunnel. Then you have a car park and the access to the car park, which are underground. And then we have a Congress Center, and you see here in this aerial view some of the structures. So here the car corridor, and this is the Congress Center. And in between all these infrastructure, they decide to place the new station. So, and the new station is there. So the new station will be composed of 3 main parts. One, the first part is a 6-story open air station, 150 meters long. Here you see a picture of what will be done, what will be when the work will be finished. Then we have the underground part. So the underground part is here. This was the open air part. The underground part is 70 meters long, where you have the platform to access to the train. And then there is an hall for the passenger transfer between the different infrastructure that we have seen some ago. So 2 different methods of construction of this station. We have a cut and cover construction method for the open air part here. You see here a photo during the works. And for the underground part, you have a conventional excavation. Here also you see some picture taken during the works. About the calendar, 4 years for the construction of the station, 1 year more for putting inside all the architectural part, and then 2024, the start of the service phase, which started earlier in May, so last month, for one part of the line. Where is located this station? Is located in the typical context of the Paris Basin. So it's a lithostratic sequence that is very well known and very well characterized because there's full of infrastructure, so it's very well defined. And as you can see, we have on top we have some rigid material. So we have limestone and marls mainly, and then at depth we have mobile soil, so sands and clay. So the station is excavated in a semi-rock ground condition at surface, and then down in the sand. And because of this geology, the construction is done using diaphragm walls. Diaphragm walls that are founded in the plastic clay. So you go down with to the plastic clay. Okay, so the work have started, and during the first construction phase, we had the construction of the diaphragm wall you see here. And this construction has been done in an alternative way to avoid an excessive unsupported section. So you construct one diaphragm panel, and then you construct the next one, not just aside, but a bit further, and then you come and you complete in between. And the excavation of the soil went down with the cut and cover method in this part of the station down to a depth of 20 meters. And during this part of the work, there was a huge monitoring system that has been put in place to check the displacement of the surrounding structure, because the surrounding structure, the metro line and the train, had to be kept in activity during the work. So we had to be sure that the settlements of this structure was compatible with the activity of these lines. So what resulted from the comparison between the monitored measure and what the initial model prediction that were not done by ITASCA, by the way, and the initial model prediction was that the settlements of the Metro Line 1, so the Metro Line 1 is this structure side of the station that is going to be constructed by cut and cover. So the settlements of this structure were higher than what as predicted by the model during the construction of the diaphragm wall. So we had a displacement of 5 millimeters, whereas the initial prediction were showing negligible impact. And also during the cut and cover of this station, the heaving of the soil, so the heaving that was experienced here, was less, has been higher than what was predicted by the simulation. So in the end, what was predicted was this blue range here. These are the different calculation phases of the construction, and this was how the settlements of this point of the station were supposed to occur. And what has been observed is that during the construction of the diaphragm wall, the settlement was higher than what has been predicted by the analysis, and during the cut and cover of the station, the heaving has been less than what has been predicted by the analysis. So what has been done is to assess the final possible displacement of this line 1, considering this new data that were gave by the monitoring system. And what appeared is that the final displacement of the line 1 may eventually exceed the threshold that was put in place for this line 1 to be kept in activity. So there was potentially a problem for the line 1 to work. So Aegis, which was the project manager, defined several assumptions which could potentially explain the difference in measure. For the higher settlement during the diaphragm wall construction, one hypothesis was the consolidation of the sand. So I forgot to tell you at the beginning, but this we have groundwater in this soil that is close to the surface. And to construct the station, you have to do a dewatering, initial dewatering. And since we have a rigid soil limestone in the top part and we have sand in the bottom part, what may happen is that the sand consolidate, so they settle down, but the rigid limestone doesn't settle down because it's rigid. And it settles down only when you cut the complete thickness of the limestone because you created the diaphragm wall. So this was one hypothesis. The other one was the construction of the panel itself, because you start with, when you construct a diaphragm wall, at the beginning you have a concrete that is not yet hardened. So you have the weight of the concrete that can create a settlement of the wall itself and the surrounding soil. And for the lower soil heaving during the cut and cover excavation, one of the hypotheses was the plastic clay, so the bottom clay layer where the diaphragm wall are founded is stiffer than expected and has a OCR higher than 1. Another hypothesis was that some of the soil layer had a K-naught coefficient higher than expected, and this might eventually limit the soil heaving. So at that point, at that point in time, Aegis contacted us and say, "Hey guys, can you create a 3D model that include the wall station, all the surrounding infrastructure, and try to better predict the settlements, and also tell us if at the end of the construction we will be below or above the threshold that is defined?" And we say, "Of course we can." And that's the way we enter in the project. So before creating the 3D model, we have started working on a 2D section that you see here. So I will show just the result for the section in the middle of the station, but we did all the job for the 3 stations. So these are 3 typical sections. And why we have started working with the 2D model was to recalibrate some material parameters for the soil. So particularly for the plastic clay that were potentially at the origin of the lower heaving. Okay, so we work with the 2D section, we recalibrate the parameters, and once this has been done, we constructed a 3D model to validate the obtained parameter set and to predict the final displacement, which was the topic of the study. But not only, also to optimize the final stage of the construction sequence, because the client started to ask, and if we do this, it will be better or it will be worse. So, okay, and the 3D model, as asked by the client, include all the open cut and the underground part of the excavation station. So we'll see later on, and then all the surrounding structure that are pre-existing. So these are just a view of the 3 sections that we studied. I show you in the next slide the sequence for the section 4, so this one. So when I present these, you have on the left, you have the geometry, and on the right, you have the evolution of the displacement. So at the beginning here, we have the metro line 1 that is here. This is a train line that exists. Here is the future place of the station. It's not yet excavated. It's just colored because to show where it will be, but it's not yet excavated. And this is the car park. Okay, so we start from initial state. We do a initial dewatering to lower the groundwater. Then we install the diaphragm wall. Next, we start an excavation. Here you see we cut that part. Then there's a horizontal pre-stressed tieback is a line of horizontal pre-stressed tieback that is put in place. So this is to prevent the further displacement of the diaphragm wall when you excavate here in between the two diaphragm walls. The excavation is going down. We put in place a first row of tieback. Then next excavation, second row of tieback, excavation again. Then we start introducing some support structure into the station, the future station. Then there's the tunnel, the TBM machine that is passing by the station. So this is the new station that is constructed, and you have the TBM that is passing through the new station here. Okay, then the TBM tunnel is backfilled with some sandy material, and the excavation continues to go down with installation of a new support structure. Then at this point, we have to go further down. The phreatic surface is here, so we have to lower the phreatic surface down to this level. Then we go to the final level of the excavation, and then we put the bottom slab, concrete slab. And at that point, we remove, you see from this step to the other, we remove some internal structure as well, the inclined tieback. Then we remove the horizontal tieback, finish to pump water, and that's it. Okay, so we have done this sequence for all the three sections that we have studied, and for different set of parameters. And this was the way we calibrate. So we obtain evolution of the displacement for a different point of the line 1 for the different cases that we analyzed. And based on this result, we have decided to select the set of parameters given by one of this case study, which was about using stiffer clay, because the displacement due to the settlement due to the construction of the wall were 6 millimeters, so very close to what has been experienced on site, which was 5 millimeters, the real displacement. And the soil heaving during the cut and cover, the first cut and cover, was also close to what has been monitored on site. So 3.5 millimeter in the model against 3 millimeter in real life. So you see that the other set of parameters give higher value of the heaving. Now we have used this set of parameters for the 3D model. So the 3D model has been created using a hybrid mesh. The concrete structure are created with block ranger, and the soil mesh using griddle. You see here all the different structure that have been created. Here you see the horizontal tiebacks, and below there's some horizontal inclined tiebacks. Okay, go on. So this is another view of the model. You can see a bit the type of the mesh, so the structured mesh in all the concrete structures. This is the metro line 1, which is one of the main objectives, and over 150 construction steps with different construction technique. I put a video here which show how it looks like. So here is the construction of the diaphragm wall. This is the underground station that is constructed. Horizontal tieback. Then you start excavating in the station with the cut and cover. Put in place slabs to ensure the stability. It's going on. It's quite a long sequence, and it requires a lot of work. So here you see the TBM is entering the station, and some point is exiting there. Yeah, get it. And okay, now the tiebacks are removed, and it's finished. So the comparison of the 3D model result with the monitored value show a very well match. So you can see that during the diaphragm wall installation, the numerical and the measurement were very close, as well as when we did the cut and cover excavation, and when the TBM passed by the station. So This allowed to validate the calibration work that we have done in 2D, and also to confirm the reliability of the 3D model for analyzing the further displacement that occur in the station construction. So this is at the end. We model all the phases of the construction of the station in 3D, and we have seen once also in real life the station was finished that the displacement predicted by the model, so the solid line, were very close to what has been monitored on the site. So you see, for example, here. This is for the settlement, and this is for the horizontal displacement. If we focus on the settlement, which was the real topic of the study, you can see that at the end of the excavation, at the end of the station construction, the displacement are very close to what has been predicted by the model. And also, the model predicted a settlement less than 10 millimeters, and it was also the case in real life. So there was no risk to overcome the threshold that was imposed. So some conclusion, we have developed a kind of complex numerical model for modeling precisely the excavation sequence of this station, taking account all the surrounding structures. One point, the monitoring system that was put in place during the excavation was very useful and allowed a calibration of the soil properties, so allowed to better anticipate the future settlements of in the surrounding structures. The calibration work has been performed in 2D, validated in 3D, and allowed to very well capture the final displacement. In the end, the model has allowed to assess also the impact of some proposed modification. I didn't have time to talk about this in this presentation, but we tested several variations of the final sequence of the construction, and so the model has been important for the client because he provided a powerful tool for taking decision about the final step of the construction. That's all on my side. Thank you very much for your attention.